Welcome everyone to the first Friday seminar of the semester on cosmology. Today we have Benjamin Joachimi from University College London. He received his PhD in astrophysics from the University of Bonn in 2010 and moved to the University of Edinburgh as a research fellow. In 2012, Benjamin received the Rutherford Fellowship, and in 2013 moved to UCL as a lecturer. Subsequently, he became a reader in 2017. Starting today, Benjamin is a full professor, which means I can assume that this will be his first international seminar as a professor. Now he will talk to us about studying cosmology with the responsible use of machines. So, Benjamin, you have the virtual floor now.
Thank you very much for the kind introduction. Yes, it's a pleasure to talk to you. It's also a shame I can't do it in person just yet. So hopefully I can do the visit at some point in the near future. But for now, it will just be the talking. What I'd like to talk to you about today is a slightly tongue-in-cheek title about the responsible use of machines. Actually, most of my research was much more sort of classic cosmology, observational cosmology, and I was going to talk about the recent cosmological analysis of the KIT survey. Fortunately, just in time I discovered you already had an excellent recent talk by Catherine on this, and so I decided to switch gear. Now, while my work was over the past couple of years was focused on kids, I'm fortunate enough to work with a couple of brilliant early career researchers, and I will unashamedly just advertise their work today. And there are a number of quite distinct pieces of work that I'm going to talk about in little chunks, up to 5, probably won't get to all of them, probably just 4. So, the sort of overarching link is indeed this responsible use of machines. So let me explain what I mean by that. So if I share screen now, again, you have to shout me down if something's not working. I assume it's all right now. I'll just happily go on. So what do I mean by this? Of course, we all know that machine learning is revolutionizing not just physics, but all areas of human interaction, very much so. But I think physics is in a very special position in that our job is to build abstract models of the universe and hence gain a deeper understanding. And so my fear is that actually a sort of bit of Wild West that we see on the archive with many analyses using deep neural networks and similar machine learning techniques popping up is counteracting that, right? It's the infamous black box that I've drawn here, right? And deep learning you could equate with shallow understanding, which counteracts what we want to do as physicists. So if you want to look at this, it's a slightly more sort of methodological perspective. If we've got here a dense network, right? In the end, it translates into what we have here. It's a very nonlinear, very flexible function with many free parameters. And most of machine learning, the real gist of it is clever techniques to actually fit these functions to a set of data, despite these very many nonlinearities and free parameters. And of course, a flexible function with many free parameters means it has little predictive power. We can learn very little physics from it. And so I would claim, therefore, these following 3 points there that a good physicist should do. And it's really a claim. I have not done deep research into this. This is my very personal opinion, and I'm happy to discuss about it. So what I think a good physicist should do is use machine learning only in parts of the analysis that are uninteresting to them. Now, what do I mean by that? It's maybe easiest explained with an example. Let's say you want to do a cosmological analysis of a survey, then how exactly systematic effects in your CCD camera are really not of interest for this high-level analysis. So I would find it legitimate that you parameterize these effects there with a machine. So you machine learn these parameters and then, for instance, marginalize the output, etc. However, if you're actually building CCD cameras, if you are an instrument scientist, you want to gain a deep understanding of what's going on in your camera, how exactly the photons generate electrons and how these electrons are transported through your chip. And so there, I think you have an obligation to try to build physical models of defects and how the electron transport works and how your potentials look like. And so there, I would argue, you want to do more standard classical model building, maybe only aided in certain parts by machine learning. Secondly, I think we should all try to keep our machine learning as shallow as possible, and then build in the physics knowledge that we have for as much as possible. Again, it helps us with actually understanding and interpreting what's going on. And of course, there are also aspects of computing time, of money associated with it, and also environmental impact, of course. And thirdly, if we have to go deep and do deep learning, then we should spend effort on trying to explain what's physically going on. And I hope to be able to show you a few examples that tick these boxes. And they will be quite distinct, and I'll try to have little breaks in between so you can ask questions about them. So I'll jump right in with the first example. It's work led by my student, Prabh Bambra, and together with Ofer Lahav. And this is an example of deep learning, and we're trying to find explanations of what this deep learning algorithm does. And the example that we're using is Galaxy Zoo, which I'm sure you've heard of. It's a citizen science project based on SDSS imaging of galaxies, and the citizen scientists were asked to classify the morphology of these galaxies. So that includes, for instance, the existence of spiral arms, bulges, bars, any special features in there. And this was then later used as the training set for machine learning challenge by Kaggle. You can see, if you follow the link, you can see the outcomes. There was a competition with a number of neural networks. A certain type of CNN has won this challenge, that then were able to classify galaxies with deep learning. And so we've also trained our own deep learning algorithm, roughly competitive with the best entries in the Kaggle challenge, and then tried to make it explain how it actually came to do these classifications. And the approach that we have taken is based on the Grad-CAM concept. I've been told I cannot give a talk about machine learning without showing pictures of cats and dogs, so I'll get over with that right now. What you see here is an example of how you can explain how classifications and machine learning work. And the general idea is that you follow back from the outputs to the input pixels and see how important a certain pixel in the image, in the original image, is for a given output. One way to do this is called guided back propagation, and that highlights edges. As you can see the outlines here. So that doesn't help us with the decision making. Decision making is whether this is a cat or a dog. And so this Grad-CAM approach here, it works on convolutional neural networks, CNNs, and it at a certain level in the structure of the CNN, it does this backpropagation. It does some clever tricks underneath there. And that way you can then highlight as an intensity map those pixels that were most important to come to the conclusion. And so you see here, for instance, that where the tiger stripes are most prominent, it decides that has to be a cat, apparently because dogs don't have these stripes. And here the face most clearly identifies this as a dog. Now let's apply this to something more useful, like a galaxy image that you see there. This galaxy was classified as having a prominent bar, a bulge, and spiral arms. And we use a version of this Grad-CAM approach called smooth grad. What that does on top of things is this backpropagation can be very unstable and very sensitive to pixel fluctuations. And of course, we tend to have very noisy images. And so what smooth grad does, it creates layers of noise, Gaussian noise on top of the image, and then pools, it averages the Grad-CAM images, and hence gets a more robust picture overall that is less sensitive to noise. And that is very useful, we found, for astronomical images. And you see here, these are the pixels most important to classify as a bar. That makes perfect sense. The bulge here in the center, and you also see very nicely highlighted the spiral arm features here. So you see that the network here starts to explain to you how it came to classify this as a bar, a bulge, or spiral arms. Now we thought, can we take this further? Can we actually make this model not just explainable, but also predictive? And Trapp managed to achieve that, and that's shown here. So here we've got a couple of images, and the bottom line here is an example where it goes horribly wrong, but in not too many cases. And we looked at bar classification, and you see here how this worked. And Trapp used a threshold in this saliency map, as they are called. So just the most prominent pixels were used, and then the linear extent of these was taken as a measure of the length of a bar. And this was compared to a measurement done directly on the images for a subset of galaxies, new galaxies, by experts, by actual physical astronomers. And you see the result plotted here. Now, of course, our smooth grad doesn't know anything about how long bars should be and where they end, so you don't expect necessarily a one-to-one relation. That would be the black line here. But if it works well, you would expect a tight correlation. And indeed, that's what we see here. So this is the correlation. Coefficient is given here. You have a few catastrophic failures. This is one of them, where it misidentifies this edge-on galaxy as one giant bar. It can happen, but overall, it does quite well. And if you compare that to a network directly trained on the bar classification, this approach actually works significantly better. So the correlation coefficient is closer to 1 significantly. And the reason is that we've used here all of the galaxies, not just a subset, which is much smaller, for the direct bar measurement. So you have used the pixel information, what the CNN learned about morphology of galaxies in general, and applied that here to learn something new that the network was never presented with, namely bar length measurements. And then another nice application we also investigated. So this is again from the original paper here, an example. So this was a network trained to classify nurses and doctors from images. And you see the standard approach here, Grad-CAM was used to identify a biased training data set. And you see here, it particularly uses hairstyles and facial features to do the classification. And it classifies both of these ladies as nurses. And the reason is simply that in the training data, most of the nurses are female, most of the doctors are male. And so it's just learned to identify human females and males rather than nurses and doctors. And yeah, once this had been identified, you could unbias or debias the model, and then it uses features of a stethoscope coming towards you or the color of the lab coat, which frankly I still find rather dubious, but here we are. So again, coming to a more useful application from my point of view, going back to the galaxy zoo, we compared what the CNN did in classification and what the consensus of the citizen scientists did. And here's a nice example where they disagree. So on the top, the citizen scientists said, this is a galaxy with features, quite convincingly, they said. And whereas our model says, this is a smooth galaxy. Now, we don't know why the human beings had that conclusion. They were told to focus on the center of the image, but maybe they took these neighbors here as part of a feature. We don't know. But you clearly see that while the network sees these, it did not consider them important, and it says this is quite a smooth galaxy. Conversely, the citizen scientists said this here is a smooth galaxy, whereas our network just about decided there is a feature in there, and also tells you where it is. You see here the high intensity pixels. So I'm not sure if that comes across well via Zoom, but there is a dark stripe or arch here around the center. It could be a dust lane perhaps. And our network has identified this and says this is a feature. I would tend to agree with that. So we are now here in the curious situation that our neural network is more explainable than the decisions of the citizen scientists. We don't know why these scientists decided that way. Right, so that was the first little bit. So I'll stop briefly and would like to ask, are there any questions on this particular project that you might have? while you're thinking, I will briefly stop sharing. So if you don't want to be shown on the stream, you may want to switch off your camera. So this helps so I can see you. So are there any questions at this point?
I don't see any hands.
Okay, all fine. And I'll go back in a moment and talk to you about the next application. Okay, should be there. Right. Next time after the project, then please just speak up. I might not be able to see you, but I'm going to pause so you can ask questions before I go on. Right, so I hope you can see this again. Can you?
Yes, we can.
Yes, yes.
Thank you. Okay, right. So onwards and upwards. So another of my students, David Ferraz, actually submitted his PhD thesis yesterday. Some momentous days for all of us. And he applied artificial intelligence to generate cosmic large-scale structures. Of course, a hot topic, and I'm pretty sure also close to the heart of people in your group. We do spend a lot of effort, time, and money in creating very large simulations of large-scale structure. So could we teach a machine to quickly generate more of these simulations? And of course, we have seen many papers in that regard already. What we are trying to do is, again, take the generative part out of the machine learning. We have plenty of examples. We have GANs and variation autoencoders, but we know how to generate random fields. And what we see out there in the universe are random fields. They're statistical realizations of, in this case, the dark matter distribution. And so this is one example that my group has worked on for a long time. On the left-hand side, you see that this is simply a log normal random field, also quite standard as a starting point for embodied simulations, for instance, either Gaussian or log normal. On the right-hand side, you see the same projection of a proper embodied simulation, which of course is very expensive to generate. A log normal random field is extremely simple and fast. It's usually limited by how fast you can write the output to disk. But you see clear differences. So we've created these fields such that they have the same two-point statistic, the same power spectrum in them, but the texture is all wrong. On the right-hand side, you see the famous cosmic web. On the left-hand side, it's not there. So we would expect that higher order statistics, which we're really keen to investigate these days, will not be right with a simple log normal random field. So can we then generate log normal random fields and then learn a mapping from the left to the right with a machine that then quickly helps us to build more realistic realizations of the large-scale structure? And it turns out that we can. So we have dedicated machine learning algorithms that are very good at learning textures. And one of them, you may have heard of it, are UNets, or residual neural networks. They have this sort of U shape that you see here, with skip connections in between. Again, I won't go into details about this. And so what we use for that here as a generator is to learn the mapping from the log normal fields to what we claim to be eventually more realistic pictures of the large-scale structure. And so what Davide did is combine this as an adversarial network with a critic or discriminator that then compares what we generated, the fake images that we make, compared to actual embodied simulation images. And you train these two networks together up until the critic is unable to distinguish between these fields. And then we have a successful generation. And as a matter of fact, we have an additional penalty term here. We also want the standard square loss of the images to be minimized on top of that. So this setup turned out to work quite well in our case. Then we have to actually create the training sample, and there David did a very nice trick. So we worked with simulations from the Quixote suite, which is specifically designed as training data for machine learning. However, we were missing nicely matching log normal fields to go with. And so the way David did it is he took the Fourier amplitudes from the simulations in such a way that we can define the power spectrum of the log normal field that we create to be the same as that of the simulation. Of course, the power spectrum is only determined by Fourier amplitudes. The phases, to make the full field, are then taken from an early snapshot of the same simulation, which is very close to a Gaussian random field. So those phases are random for a Gaussian random field, but it's a particular realization that, of course, then evolves to the low redshift of the universe eventually. But we can use those to create a similar pattern of structures to begin with in our log normal field. And with these pairs, we can train the algorithm, and this is the outcome. So on the left-hand side, we now have the accurate embodied simulation. And on the right-hand side, we have a generated map from our algorithm. So you see the cosmic web is there. There's some similarity of structures, but you don't expect them to be identical. For instance, here we've got an overdensity that is also reproduced here. So that memory comes from using the Gaussian phases from the early snapshot. But again, we don't care that much for pretty pictures. It's the statistics that we really care for. And so looking at that, here are a couple of plots on this and the next slide. And what you need to look out for are the three colors. So orange kind of is a log normal statistic from the log normal field. Then brownish is from the embodied simulation, and turquoise from the prediction. So you want the brown and the turquoise to be close together for the method to be successful. And it will be distinct from the log normal. And we see indeed that happens. So these are the simple counts. This is the P1 point PDF of the dark matter density contrast, and you see quite close to each other. The power spectra all match, and that's by the design, by the way we trained, created the training data. But the interesting bit now is what comes here, the higher order statistics. On the left-hand side, we have peak counts in the projected field, and you see indeed it's very nicely and close to the embodied simulation. And here is one particular configuration of a bispectrum, so a 3-point statistic. And again, you see it's not perfect, but it's very definitely much closer to the embodied simulation. And so that has been successful. I don't think we'll stop here. I think we can put in more physics eventually, but it's a very good start. More physics, for instance, could come from the fact that we know how particles actually move. We can, for instance, derive gradients of the dark matter field. There's some interesting work that has recently been published on this. This information can probably be inserted into that methodology as well. Okay, that was my quick snapshot on this project. So again, I pause briefly if there's a question directly on this.
So yeah, I have a question. It's very noisy here, sorry. But can you say a few words about what applications you have in mind with this?
Okay, so ultimately an application I have in mind is that we use log normal field generator that can be in 3D as we have for initial conditions of embodied simulations, or in 2D shells like a Flask algorithm that we developed a while ago. And if we then combine that with this methodology, you can create log normal random fields, let's say in shells in this particular case. You apply the algorithm and turn the log normal random field into something that looks quite close to the actual large-scale matter distribution. And this can then an ultra-fast way of creating mocks that can be used, for instance, in likelihood-free inference or for validation of pipelines.
What about covariances?
Yeah, absolutely. We've looked at 3-point statistics. To get the covariance right, you would want 4-point statistics to be in there as well. And it should work. We actually have looked at this in a slightly different project. And yes, it seems to work for that as well. It's a good point, yeah.
Okay.
Hey, good.
Thanks. Thanks, Ben. That's very impressive. I just wanted to ask, now you said that I'm not sure I understood quite correctly, but the power spectrum is sort of tuned in the
Yes.
image. But what about different cosmological parameters? If you change that, how do you change the contrast? You know, in the image, it looked like in the example you showed, it was more, I would say, voidy. Now, that's a higher order statistic, obviously, but is that something that's dependent on you know, the input cosmology?
Absolutely, yes. That is a very good point that we have not addressed yet, but need to. You're absolutely right. So I think you're alluding to this, and I agree. For my eyes, the right-hand side looks different as well. But as we've seen, the 1, 2, and 3 point statistics seem to match. So maybe it's just an illusion in this case that they are systematically different. But you're absolutely right. So if you want this to work in general, you will have to condition this network on initially redshift. That's what we're working on right now. Right? You want to be able to do this for all kinds of redshift. And of course, large structure evolves. And then you need to condition it on cosmology as well. Now, we had some brilliant ideas with this tuning of the power spectrum. Now, the power spectrum contains, we know, a lot of cosmological information already. So if we can take that out, if we can tune things to match, we would expect that the cosmology dependence should be much lower. However, in the current implementation, we're not quite there yet. It turns out that the neural network really likes the power to be in these fields to be able to learn this better. And so that idea that we can suppress the cosmology dependence that way didn't quite work out yet. But this is one of the things where I think more physics can be put in, and so we can reduce the cosmology dependence so that can be learned more easily. But you're absolutely right, that needs to be done.
Yeah, it's really very impressive. I'm blown away because, of course, I spend a lot of time, you know, using a lot of cycles to produce such images, you know, with the true M body. And yeah, I was wondering, could you have a link? Will you provide a link for the software that you're using? Is this public? Can people play around with this already?
You certainly will be. So I'm showing you something that is very, very hot off the press. My post-student had to submit his PhD thesis, but as of today, he can write up this paper, and we hope for this to be on the archive within the next couple of months or so. And from that point onwards, we're surely happy to share the algorithm that he used.
Great. And just one more final thing. Maybe this is, I guess, is it something that you're going to present at the simulation working group? This would be quite fascinating.
Yeah, I'm happy to ask David to do that. I'm sure he'd be very happy.
Great. Okay, that's it. Thanks.
Great. Okay, so I suggest I rush on.
Jayul? Sorry, Jayul had a question.
Yeah, okay. So my question is actually partly answered by you know, Joachim's question, I think. So I was just you know, to clarify, I mean, to train your neural network, you need a series of n-body, really the correct answers, right, for a given cosmological parameters, right? So if you want to use like you know, likelihood analysis and so on, then you need really a lot of a set of outputs for different cosmological parameters. So in this case, I mean, you already mentioned, but then so to have a reliable prediction from your neural network, you need to train with a different set of cosmological parameters.
Eventually, yes.
Okay, at this stage, right? Maybe future is better.
Yeah.
But in that case, probably, I mean, the cost of training this neural network is maybe as large as just running simulations with the different cosmological parameters.
I don't think so. I can't tell you a number, but I would expect there's still a very substantial gain right now. And also, we're working with the Quixote suite that is out there in public, right? So it's been created once, and as long as we find it is sufficient for our purposes, and for now it looks really very suitable, that effort has been done.
Okay, so maybe I misunderstood. Then you have an initial set, the initial condition at high redshift of your n-body simulation, and then the final output at the low redshift, and that's all you need for the training.
Yeah, correct.
Aha, okay, so just the one simulation run for one cosmological parameter set.
Yeah, so what we got from Quixote is redshift 0 or 0.5 or 1, so low redshift snapshots. And then we also have one at the initial redshift where they started running the simulation, which happens to be 127.
Okay.
And so these pairs is all we need. And then this clever trick to get the actual log normal field to create a pair for training.
Aha, okay. Got it. Thank you.
Okay, great. Thank you. Okay, so changing tack again. This is now much more closely related to the actual observation, and it's learning systematics in the survey data. And again, that's a complicated business, but extremely relevant. So just to say, again, this is published work. You can follow it up. I've put the link there, done by my fantastic former PhD student, Harry Johnston, who is now a postdoc in Utrecht. So what you see here is a map of the kilodegree survey. You have the northern field and the southern field. And what you see here is the galaxy distribution mapped. Now that probably doesn't look like what you would expect, and it doesn't look very cosmological. Rather, it looks much more checkerboard. What we've done here is mapping actually systematic quantities, what we call housekeeping quantities. So this is the size of the point spread function. It gives you an idea of the seeing. This would be the ellipticity of this point spread function, and this is the depth of the survey, for instance, determined by the background noise. And what you see there is very distinct patterns. Here you see the pointings of kids, 1 square degree patches. If you squint closely, you might be able to see actually the pattern of the focal plane. You can sort of circular structures within the pointings. And you also see a systematic variation between kids north and south, which is linked to the fact that you're looking at different galactic latitudes. You might have different observing conditions at different times of year, parallel. All of these things you see there, but certainly not a cosmological galaxy distribution as such. So these effects create systematic patterns in the sky. If you measure the correlation function of that, you will get a very interesting signal, which has nothing to do with cosmology, but might be of similar size or even larger. So we need to be able to correct for this, of course, not just for kids, but also for Euclid, if we do photometry, and for LSST, etc., etc. So how do we do this? It's very difficult to get a physical model of this. So this might be an example where machine learning can really come to our rescue. And it turns out a very old school method is very useful for that. So self-organizing maps or SOMs. They are quite old school. They're much more fancy modern methods around. What we found is the reason why they are so loved in astronomy is they're very robust to noise. If you expose the modern algorithms, dimensionality reduction algorithms, to the noise levels that we typically have in our field, they all crumble and perish, whereas the SOM is quite robust. So I think that is actually the reason why it's so good. So what it does, it's a neural network that maps from a high dimensional space to a 2-dimensional space, preserving the topology of the whole space. And so taking the 3 systematics that I showed you on the previous map, they are mapped now on 2D, and you see here in red and blue the values of these respective systematics. Red usually means bad for the survey, blue means good here. So this would be a particularly shallow part of the survey ends up here in this abstract space, and this would be particularly bad seeing and good seeing. And then you can relate that to the relative galaxy number density, so higher or lower than average. And what you see here is what you would actually expect. Here we've got an area with slightly below average galaxy density, and that is linked to the survey being a bit shallower, and then also in particular to have bad seeing. And conversely, you get deeper surveys here in this part where you have low background, but also relatively good seeing, and ellipticity is less relevant in this case. So this is what the SOM can tell you. By reducing the dimensionality of the whole problem, we can actually use redundant parts of the survey starting to distinguish between the cosmological fluctuations of galaxy density and the ones created by observational effects. And so if you combine all that together, you can create a random catalog. And if you use that in clustering, you take out all these systematic trends. So this is the combined catalog of all systematics effect. You again see the pointings, the little squares everywhere. you see a systematic difference between the north and the south, as we already could guess from the initial maps. And then we combine it with another neat trick. That's not our idea. That was developed for the Gamma survey. Sean Cole and others are behind this. That is cloning galaxies. So instead of just creating random points, you assign each of these points the properties of the real galaxies, properties like their colors, magnitudes, whatnot, everything you can think of and that is relevant. And you do that in proportion. And that means you can then later on select on these galaxy properties, also in the random, and hence work with subsamples in any way you like, but you only ever need to create one random catalog. So that saves an enormous amount of pain. And you see the effect, for instance, here. It's quite subtle, but you can just about see it. If we, for instance, select blue and red kids galaxies, you see that the randoms here at this particular right ascension have a systematic difference. So for some reason, probably depth in different bands, blue galaxies here are expected to be a bit sparse on average. So you have lower density in the random catalog, and that should then remove this systematic trend here with galaxy color. So just a quick look of how that performs. These are clustering measurements. It's done on simulations that have been populated with the actual kids survey systematics, and then we see how well we can remove them. And suffice to say that if you're close to the one-to-one line, that means you have succeeded. And these are different setups of the resolution of the self-organizing map and other sort of subtle features of the methodology. We see that for all the default ones here, we're doing quite well in removing systematics and bringing what used to be up here at this level back down to where it should be. This was done on a bright subsample for kids, and it's a published work, and we have since applied it to deeper data, to essentially the full kids data. And there's a very nice effect here. Since this is data-driven, right? This is an unsupervised approach, so it learns the patterns from the galaxies. You get better the deeper the sample is. You have more galaxies in there, and hence you have more chance of actually learning systematics from the data. And the performance for the deeper survey, where the systematics are even worse, is actually quite good. And so hopefully there will be a paper led by Angus Wright, who's also involved in this, a postdoc in Bochum, where he shows that we can even do this for deep data, which will be of similar depth as Euclid, for instance. Yeah. So this is, again, quite an interesting application of very simple old school machine learning, which can be really beneficial for us. And looking at time, I'll briefly talk about one more point, which actually has some relation. There's also some in there, and led by another of my PhD students, Benjamin Stölzner, and that's in the context of the LSST dark energy science collaboration, but it's applicable for all kinds of galaxy surveys. And the idea is to put galaxies into their place. Of course, as you're probably aware, we have lots of imaging surveys, and we have to use photometric redshifts to actually get the third dimension of our survey right. We cannot do spectroscopy for everything. The way we usually do is we take the colors and have then photometric redshift estimates of various provenance, including machine learning. And so what we then do is we define disjoint bins of these photoset estimates, given here for kids, and here it's for this, a similar story there, and in the hope that this creates reasonably disjoint samples of galaxies, so we get shells along the line of sight. That works to a limited degree. As you can see, the actual distributions, getting those is a science by itself. I'm not going to talk about that. It's not exactly disjoint. You see there's a lot of scatter, you get broad distributions, you get shoulders and even outlier populations, as for instance here, and there's some very small ones hidden here at high redshift as well. So the real situation is a little messy. And for the LSST, it would be particularly tricky because it's a very, very deep survey, and you don't have very, very deep infrared colors. So the performance here might be much worse. However, there is additional information to galaxy colors, and that is clustering. So if you've got an overlapping spectroscopic reference sample, it doesn't have to be representative. You can measure cross-correlations, and you expect there to be zero cross-correlations if there are no galaxies, and you do expect a signal the more overlap there is. So taking the example of the fourth bin, which gives you this greenish distribution, and then measuring cross correlations. This was done here by a KIDS 1000 paper not long ago. You see actually that you start to recover this distribution, of course, with error bars, and I'm hiding a lot of complications regarding galaxy bias evolution, etc. from you. But in principle, you can use these to validate the distributions. Now, wouldn't it be nice if one could use that information to also define more compact bins in the first place? Well, there you have a bit of a chicken and egg problem. Of course, you need typically thousands of galaxies to measure a clustering signal in the first place. So we have to define a sample to measure the clustering, but that's the sample that we want to define in the first place. So in principle, you could just position galaxies randomly along the left side, define samples, measure the clustering, then try a different random combination of galaxies and see whether the clustering looks more like a disjoint binning of galaxies. Now, that's of course a preposterous algorithm to do. We want to do this for hundreds of millions of galaxies, and we can't just randomly place them around. That even Deep Blue and AlphaGo cannot do this for you. However, fortunately, I have a brilliant PhD student who can do this. So here's the algorithm that we developed that actually manages to do this, to use the clustering information to create more compact bins. And so very briefly talk you through this. So you start with the colors as usual. You can derive a photoset estimate. You put all this information into a self-organizing map. We've seen that before. This time it's the space of all the colors, the multi-band photometry that you've got. For KIDS, that's 9-dimensional. For LSST, it's 6-dimensional. So we've done that here. The different colors correspond to different redshifts. And then we can cluster in this 2-dimensional space. We can create clusters, not galaxy clusters, clusters in this abstract SOM space. So those are then galaxies that have very similar color. And we can do this hierarchically, as illustrated here. So we start with a relatively coarse clustering, few clusters, and then we start to move these clusters and assign them to new tomographic bins. Then we measure the clustering and use a very classic old school physics motivated algorithm, and we simulated annealing that's very good at finding global minimum, to then shuffle these clusters around and find an optimal solution. And so the analogy here is with energy, and so the energy is calculated to maximize the autocorrelations, so where you actually want your galaxies to be, and minimize everything that's out of band. And so gradually then you lower the temperature of the algorithm, which doesn't allow it to jump out of local minima as much as initially, and then it should converge to a global minimum. So we run this algorithm for a while, and I'll show you what we get. So again, this is the SOM. We have binned it into 11 tomographic bins. -1 means it hasn't been assigned at all. There are just very few of those. And this is cheating. This is taking the truth. This is taken from an LSST simulation. So this is the ideal of what it should look like. If we use photometric redshift, so the standard approach, that's what it looks like. So you see, for instance, very high redshift bins in dark red haven't been assigned at all, they have been missed. And you also see shifts here in these transition regions between very low and high redshift. So that happens when you've got spectral features that can be confused. For instance, the 4000 angstrom break versus the Lyman alpha break. So these are all the things that go wrong. They lead to catastrophic outliers, and of course, there's a lot of scatter in there as well. If we run the new algorithm, we get to this. Again, there's noise, it's not perfect. You could run it for longer, but it looks much better already. So if I go back one more time and you can flick, this is the truth. That's the standard. This is what our algorithm does. So to show you what that really looks like, well, these are the changes, and you see some galaxies are actually shifted from all the way to low redshift to high redshift, or actually vice versa, by almost 10 bins. And you see this happens particularly where you've got this confusion between low and high redshift, for instance. And it goes the right way. And so this is what you end up with. These are the 11 bins that we have defined. You have got the dotted lines are the distributions that you traditionally get from just binning by your photometric redshift estimate. And the solid lines are after running the algorithm. So it's very busy, but if you just take a step back and look at it, you see that the solid lines are generally higher in the peaks, so they're more compact. They lie more here within these dotted lines where they're actually supposed to be. And you see in particular that outlier peaks have been suppressed. And that happens particularly at high redshift, where it gets really difficult with optical data to distinguish it. So look, for instance, at bin 9, which is this light green or whatever. You have a big outlier peak here due to confusing of spectral features, and that gets suppressed down here, and you get a lot more galaxies where they're actually supposed to be. At very high redshift, that's the whole bin, everything above redshift 2. Initially, there's actually very little true galaxies above redshift 2. You have a whole bump here where they're not supposed to be. All of that gets reduced and it gets pushed out to where it actually is supposed to be. And so this, again, you could run it for longer, and we have an expectation that this should do it better. And all distributions actually have more probability mass within the original defined bin, and that gives you a more disjoint binning of galaxies in redshift, and hence higher signal noise, for instance, in galaxy population. And in particular, you have managed to get rid of large outlier populations, which make your analysis a real pain. Okay, so I suggest I stop here. I will not tell you more about emulators, but I know in the Zurich group, I'm preaching to the converted. You have worked on this yourself. They are surrogate models, very useful machine learning. We're not avoiding knowledge. These are things, mappings from A to B that we already understand physically. We use the emulators to speed up the process and hence enable new ways of inference. And we apply this to cosmology. It's a Cosmo Power project that you might have heard. And what might be less known is we've also applied it to the case of seismology to find hypocenters of earthquakes in this case. But again, no time today. So let me finish on this with my main message again. Machines are extremely useful. We should use them to support the physics, the way we build models, but they should not be used to replace physicists. We all want to keep our jobs. So no more black boxes. And the examples I've given, like saliency mapping, like generative models, but the generative part is still done by the physicists, the data-driven signal separation of systematics and cosmological signals, and these giant sorting problems, as well as emulators, are all hopefully useful examples. So thank you very much.
So Sambit, do you want to lead the questions?
Yes, yeah. If you have any question, you can raise your hands and can keep an eye on them, or you can speak up. Yeah, you okay? All right.
Okay, yeah, I just had a question on the last part with the binning and the clustering, the color clustering that you're using. So you mentioned that you're improving the signal to noise. Have you looked at improvements in the, in the output from, say, Euclid's photo Z plus, could you use this there? And what effect would it have on photometric galaxy clustering?
Yes, so we haven't looked explicitly at Euclid, but there's no reason to expect that it wouldn't help there as well. So actually our cost function that we minimize with the algorithm is essentially that, because we're adding up the clustering signal of the autocorrelations and we're subtracting the signal of the cross correlations. And so that is essentially a measure of how much signal you have in the clustering. And that is what we actually maximize in this case, minimize the negative of it. So there are quite substantial gains in this. Plus, as I mentioned, the fact that you have catastrophic outliers creates a whole lot of problems, right? So you now have completely disjoint populations that you have to model together in terms of galaxy bias, for instance. And so by especially suppressing these outlier tails, you make your life quite a bit easier.
Okay, thank you.
Johannes?
Yes, hello. So I guess the method you presented you would call responsible in your framework. So what would you say is a non-responsible or an irresponsible use of machine learning in physics?
Yes, right. So let me clarify. I've done that as well. So I'm guilty of being irresponsible with machine learning as well. So okay, maybe A couple of obvious examples would be where you use deep learning to do a classification or regression. And you just run with it. So, right, you just say, well, okay, I've trained it, I've validated it, looks fine, let's go with it. And I would argue that's not what we should do, right? If we have built a new model and it's extremely flexible, so it's not very predictive, we have a duty, if you want, to understand and explain what actually went on here. And there are different ways. We used saliency mapping. There are other new ideas like symbolic regression, where you essentially prune away from your network until you just have the relevant bits in there. And that hopefully helps you to get something that's actually much more explainable and gives an interpretation of what's going on. So this is by no means the only way. But I think this has to be a necessary part. Currently, I see a lot of papers that just stop at, yeah, it works, here's the paper. I want to know why it works. I'd rather have something that doesn't work quite as well, but I really understand how it works. Does that make sense?
Yeah, I guess. Thanks.
Yeah, and again, of course, if you look into more the fields of machine learning, computer science, this explainability and interpretability is a big topic. So it's not just physics, right? So, and I think physicists can make a useful contribution here, because this is our job, right, to interpret things and find these interpretations. So I think that there's something for us to also give to other fields potentially.
So I just jump in there quickly. So I accept all of that, and I think it's true. However, what would be an irresponsible emulator? I mean, does it even matter there in this context?
Yeah, again, I didn't have much time to talk about, sadly, but I think, no, with emulators, right, you can go all out, because
right. Okay.
Right, you have, what they do is, right, you have an n-body simulation where you put in physics, right, there's no black box there, it's just computationally intensive, or you have your Boltzmann code, right, you know exactly what it does, and this is just convenience, right, you're just creating a fast bypass to it. So yeah, for emulators, I think you can throw everything at it that you like.
Good.
Can I add to this?
Yeah, please.
Because you had this very simple problem before, where you had that the nurses were misidentified, right, as just being women. Couldn't a similar thing happen in emulators, where the network interprets the important features of the simulation as the wrong ones and then only produces these, and some class of the simulation gets lost?
That could happen, but you would identify this, right, with your emulator, because you have, in the classic way, you have extracted the predictions, like the matter power spectrum, and if you miss the key features, you will not be able to reproduce that. So unless your validation is insufficient,
yes,
it should not happen.
Okay. So how do you check if the validation is sufficient?
Yeah, that's a whole other business, of course. Yes.
Okay.
I mean, right, yeah. Representative samples, etc. Right. So yeah, that's not trivial. Many cases, it's really hard to get
right. I don't see any hands. Maybe I can ask a very generic question. You initially said that we should keep our networks shallow and try to understand what they physically give us. But how do you weight with the training set or the data set that you have? Because if you have small data set with a shallow network, you can learn shallow features and get very good efficiency, but in a bigger data set, you might have more information, which you might lose. So how do you weigh uh, your shallowness?
I would argue you don't lose the advantage of if you've got a huge amount of training data, but you just make your shallow learning even better validated, right? If you've got lots of data to actually check it and all parts of it. So that's always good. But you gain a lot, because if your learning is shallow, you've put in already a lot of physics, so you know how to interpret it, and your model necessarily becomes more predictive, right? It's Occam's razor at work. So I think it's always an advantage if you can do it.
Hey, I have one more question about this your neural network generating n-body simulation output at the low redshift. So you have only the initial, the information at the high redshift, and then the information at the final redshift, and then you train your data, and then you produce multiple outputs at the low redshift, and then you measure the power spectrum. It turns out they work pretty well, right? But if I remember correctly, the deviation was like a 10% level, which is very good. But what is the limiting factor? If we want to increase the precision, what do we have to do?
Right, so you're absolutely right. On the power spectrum on larger scales, so low K, there was this 10% deviation. We think, my student thinks he understands where that is coming from. So this is just, we're not quite consistent in the way, so we're looking at 2D slices here. And so there's a non-commutativity between projecting the box and measuring the power spectrum. And I think for the results that we've seen, he's still doing it the wrong way around. So he's convinced that once he fixes that, which is easy to do, that these 10% will become much, much smaller. So beyond that, I think there's no reason to be able to be much more accurate in the power spectrum as well. And we should be, right? For this to be useful, I think we have to be at a few percent level. For instance, if we want to use this to calculate covariances, we don't have to be sub-percent, but we have to be a few percent, 2-3% probably in the end.
But in this case, what do we have to do? I mean, we generate more log normal mark samples and then train more, or is that what we need to do?
Well, optimistically, I would say if we fix that little issue that I mentioned, this should go away. We should probably be in that region already. Beyond that, again, is again, I think, ideally what I would like to focus on is not more training. Again, that makes the network deeper. I don't want to do that. Is rather doing cleverer training. So we have already this nice scheme of building the training pairs. As I mentioned, we initially had the idea of creating fields that have the power taken out. So you go to Fourier space, normalize the Fourier amplitudes, go back to real space. So you essentially, right, so you have very little power in there, but you still have the cosmic web in there, which is dominated by the phases. That nice idea didn't work because the networks, at least as we used them, didn't like it. They prefer the contrast that you get from putting the power in. So if we can optimize our network structure, that it's actually happy with learning that, then we have exact power spectra in there because we've taken all fluctuations out. They're exactly the same. And you can then impose any power spectrum on top that you like by just introducing new Fourier amplitudes. So I think that would be, if the accuracy isn't good enough, that would be my first avenue to try to reproduce that. Going beyond this, there are more ideas. For instance, there has been very interesting theoretical work over the past 20 years on the distribution of Fourier phases. So we know they have the sort of sinusoidal-like distributions over the phases, but we're looking at phase differences with a characteristic pattern that you can either characterize perturbatively, so you can specify a bispectrum, for instance, that gives you an idea, or they're sort of more global prescriptions, which again look normal motivated. And so you could, in principle, rather than learning maps, you could go much shallower and just learn these Fourier phase differences distributions and use that for generating. That would be fantastic if we can get that to work, but that's a bit longer in the future.
Okay, thanks.
Is there any more question? I don't see any more raised hands. We can stop the session now. Let's thank Benjamin again.
Yeah, my pleasure.